Hello, everyone. My name is Anderson Sasaki. I'm a software engineer at Red Hat. And currently, I'm working also as the upstream tech lead, let's say, of Keylime. And in this talk, I will talk about some changes we are making to Keylime so that it makes it better, let's say, for the edge use case, IoT and cloud as well. So here is the agenda. I will give an introduction. Hopefully, it will be quick to go through what is remote attestation and how Keylime works. Then I will show what is the current situation and why it's not so nice for the edge case. Then I will show the future or what we are working on to make it better. And finally, I will quickly talk how open source made all of this possible. So first thing, what's remote attestation? So the short one-sentence description is a mechanism to check if nobody modified your remote machine. So the long answer is that is a cryptographic mechanism that allows you to assess the integrity and authenticity of the state of a remote machine. So it relies on a hardware root of trust. Usually it is a TPM or a TE if it's based on the processor. So here I try to illustrate. So imagine this is a machine you want to attest. So you have all this piece of software from the firmware, which loads the bootloader, which loads the kernel, and so on. So the attester is the piece of software that measures the whole state of the machine and puts it into our hardware root of trust. And from there, the hardware root of trust can generate signed evidence, which is a proof of the state that you had in that machine. This evidence is verifiable, so you can check cryptographically that the content there is what you expected or not, right? It's just evidence. So this first part is the role of the attester to measure the state of the machine. So the second role is the verifier. This is a remote entity which you configure through policies. So basically, the policies tell you how you should be verifying the attestation evidences. You also need some endorsements, which are basically extra material that helps you check the trustworthiness of the evidence you are checking. This could be, for example, CA certificates that you obtain from the manufacturer or the hardware vendor that allows you to check the trustworthiness of the evidence. Then it comes the evidence with the measurements. The verifier follows the policy to verify the evidence using the endorsements as extra material to verify the trustworthiness of that evidence. Then the verifier generates an attestation result, which is, let's say, a certificate that the evidence passed or not the attestation, depending on the measurements there. So if it basically matched what you expected, then you can say the attestation result it passed the attestation, and it generates a positive attestation result. So who uses the attestation result is called the relying party. So this can be any application that wants to modify its behavior depending on the result of the attestation, if it passed or not. So it is also configured by policies, which basically means what should you do if the attestation failed or if the attestation passed. So then you receive the attestation result from the verifier, like a trusted verifier, and you can make a decision on what to do if you want to change a behavior or not. So that's the relying part role. So it's a consumer of the attestation result from the verifier. So that is all for the remote attestation part. Now comes Keylime. What is Keylime? Keylime is a remote attestation framework based on the TPM, the Trusted Platform module. It is a project in Sandbox, project in CNCF. It provides runtime and measure boot attestation. And for that, it uses two technologies, the Linux IMA, or Integrity Measurement Architecture, and the UEFI measurements during the boot, so that it can verify all the pieces that were involved during boot. So again, the Trusted Platform module, what is it? It's a piece of hardware or firmware that is installed in the monitor machine. It's what we call the hardware root of trust. It contains some specific characteristics. One is that it contains the endorsement key, which has an endorsement key certificate, the EK certificate, that is signed by the manufacturer when it manufactured the chip, basically. And this certificate is immutable, so you cannot change or replace it in any way. So it's basically read-only and written, burned down into the chip. This EK certificate can be used as unique identity for the TPM device, and we use that to identify the machine. Another part of the TPM that is very important for us are the PCRs, so the platform configuration registers. They are special registers inside the TPM, the hardware, that is used to store the measurements obtained by the UEFI during boot and by IMA during runtime. So the extend operation is this operation that you take the PCR current value of the stored in the PCR, extend it or append it with the new measurement, and you calculate the hash on top of it. So you have like a rolling hash containing all the measurements, and this kind of can be seen as similar to a Merkle tree. So the final state of the PCR value, it depends on all previous states of the PCR value. And the TPM can generate what we call the quotes, which are signed snapshots of the PCR values. So basically, is that what we use as the main evidence, because you can verify the signature there in the PCR using the certificate provided by the manufacturer. So here I will illustrate quickly the extend operation. So we start with the initial value of the PCR. So you append there the measurement of the firmware, for example. Then you put it as input for the hash function. Then you generate the new value of the PCR and repeat it again for the next part of the bootloader, for example, the boot process, and so on. And in the end, you have a state in the PCR that depends on all previous states. So it can be seen as a summary of the whole history of values that were extended to the PCR. So the UEFI, if you are not familiar, is a replacement for the BIOS firmware interface. Is basically the first piece of software that's executed during boot. And what matters to us in Keylime is that it measures every event that happens during boot, which means measuring all the images that it loads and extends it in specific PCRs. So the UEFI uses the PCRs from 0 to 9, and each set of events goes into one of those PCRs. So basically, during boot, every piece of software that is loaded to be executed is measured into a PCR and using the extend operation, and you have in the end a value that is basically a summary of the whole history of all the events that happened in that boot process. So the Linux IMA is a subsystem in the kernel that measures the files in the file system as they are opened, or read, and loaded to be executed. And it follows a policy, so you can configure what kernel will measure there. So usually you make it to basically measure all executables, files owned by root, configuration files, and so on. So basically the things that matter to you should go there in the policy so that IMA will measure it and extend to the PCR. So IMA uses the PCR number 10, and it generates a log of events which contains all the files that were measured and their respective hashes and so on. So the important part is that in the end you have this log of events that you can replay. So basically you calculate the extend operations following the log, and then you can check in the end if the value that you calculated matches what you received as a measurement, and then you have a way to verify the integrity of the file system. So during the execution, there are these steps in the boot process until it reaches the runtime. The first part in the boot process is measured by UEFI and extended into the TPM. The runtime is taken care by the kernel IMA, which uses the PCR extend operation to measure it into the PCR values in the TPM. So enough of introduction. So why this talk? The goal of this talk is to explain what were the problems we were seeing, especially for the edge, IoT, and cloud use cases, which the current architecture of Keylime is not really a good fit. So Keylime currently runs in a verifier-driven approach, or you can call it a pool model approach, which means the server or the verifier initiates the attestation. So you have a server that will reach out to every agent enrolled to ask for the measurements actively. So we are making changes to make the Keylime to work in an agent-driven model or push model, where the agent is the part that will initiate the attestation process. So first, the verifier-driven attestation. The current state is that the verifier initiates the attestation by requesting periodically the agent state or the agent measurements, the evidences. And this requires the verifier to actively make requests to each enrolled agent. So by default, it's like 2 seconds. So every 2 seconds, the verifier has to reach out to each enrolled agent and ask for the measurement. So here I illustrate what is the current situation. In the left-hand side, you have the machine that you want to attest or monitor with the agent running there. It has access to the TPM hardware to get the measurements. And the right-hand side, you have the verifier running in some trusted environment. So first step, the verifier initiates the attestation, requesting the state to the agent. The agent will request the quote to the TPM, get back the signed quote, and send it to the verifier with the IMA and UEFI logs, so that the verifier can replay those logs and verify if the values match what you expected. And so it verifies the attestation and makes a decision if that's okay, it was what you expected, and it matches the policy, then okay, nothing happens basically. And in 2 seconds, the verifier will request again another state, another measurement. But if not, then the verifier will react, basically triggering what is called the revocation infrastructure in Keylime, which can notify a configured webhook about this attestation failure. And this revocation mechanism also sends a notification to all agents So initially, the idea was that the agent could react to the failure of a peer. So if you imagine a cluster with many nodes running the agents, if one of them failed attestation, the other agents could react, for example, cutting it off from the cluster or something like that. So this is the revocation mechanism. So what are the main issues with the pool model? Each agent runs a complete web server. So this complicates the deployment. It is necessary to configure the firewall, the network, for every node that is monitored. If it's behind a NAT, then like additional routing is necessary, so it's not so easy to reach to the agents that you want to measure. So for many enterprises, this is completely unacceptable. So running a web server in each node and open up ports on the firewall doesn't sound nice, and it increased too much the attack surface for the enterprise. So this is unacceptable. And also, it's difficult to handle the situation when the agent loses connectivity. It can be temporary, or maybe simply the network is low and the verifier doesn't get the measurement in time it expects. So it's difficult to decide, okay, now I'm giving up, I'm not measuring this agent anymore. And then later, if you want to go back to monitor an agent, you need like to intervene there and do something to re-enroll the agent back to be monitored. So it needs this active action from the administrator, someone to make the agent to get back to the monitoring. So the new way is the agent-driven attestation. So of course, this means that the agent will initiate attestation, but this also includes two big changes. One is that we included a new authentication mechanism in the proposal, and we also have a capability negotiation from the agent, so that the agent can negotiate with the verifier which kinds of evidences and with which parameters it should send. So you can see this negotiation as a way to, in future, support other kinds of attestation evidences. For example, if we include TE attestation reports, trusted execution environment attestation reports, then it could be a way to have there. So the proof of possession authentication, this new authentication method, it uses the keys inside the TPM as a way to authenticate the agent. So it starts with the agent offering to the verifier what are the authentication methods it supports. So for now, the only authentication method is the proof of possession, but the idea is that it is extensible, so in future we can add other authentication mechanisms. But then, so the agent offers which authentication methods it supports. The verifier will choose what authentication and with what parameters, and will also send a challenge, which is basically a randomly generated nonce that should be signed by the agent, so as a challenge response. The agent sends the proof of possession, which is the result of this operation called TPM-to-certify, which basically signs a public part of some object inside the TPM, together with the qualifying data. In this case is the nonce, the challenge, and sign it all together with the AK, the attestation key, which can be verified to authenticate it and verify that the agent really has access to that specific TPM with that AK inside the TPM. So again, we have this situation. You have a monitored system. You want to measure it with the agent. But now, who starts the process is the agents offering the authentication parameters to the verifier. The verifier will choose some parameters and send also a challenge. The agent will ask the TPM via the TPM to certify operation to sign some key together with the qualifying data, which is the nonce, and get a challenge response and send back to the verifier this challenge response. The verifier can check that that is really signed by that TPM, and if everything is okay, send back an authentication token, which should be sent together with the following requests. So we added also with the agent authenticated, then it can start the actual attestation process. First step is the capabilities negotiation, which basically the agent goes through a very similar process of offering what it's capable of providing to the verifier as evidences. For example, now it supports the TPM quote, right? Plus the IMA logs and the UEFI logs. And the verifier can choose which algorithm it wants it to be signed and so on, depending on the capabilities of the TPM and the capabilities of the agent. And then the verifier will choose the parameters. And this can be seen as a preparation to receive other types of evidence in future. So if we add some hypothetical plugin in future that can generate trusted execution environment attestation report and send back to the verifier, this would be where it offers this possibility and it can select it. Then the verifier sends the selection back to the agent. Then the agent can prepare those evidences following the parameters that were selected by the verifier and send periodically the evidences to the verifier. So in case of attestation failure, the verifier can notify the configured webhook about this event so that it can react to this attestation failure. So same situation again. We have on the left-hand side the agent, the monitored system, and the verifier. So first step, the agent will offer the capabilities, which is basically offering which evidences the verifier wants to receive and with which algorithms and etc. The verifier will select a set of the evidences and its parameters following the configured policy, right? Then the agent will get a quote from the TPM, send back to the verifier with the IMA and UEFI log if it was requested during the negotiation. The verifier can verify the attestation. If it's okay, nothing happens. It will wait again for the agent for the next measurement. If not, then it will react, notifying the configured webhook. So this is what will happen in the new, so the expected is that the agent will periodically send a new quote and the verifier will verify it and so on. So what are the advantages in this case? So it's much easier to deploy because now instead of having to have an agent which has a complete web server, which needs special firewall configuration and so on, you just have a client that will push data outside. So normally the access to the external resources is allowed in the rules. So it's much easier. It is easier to handle the intermittent connection loss. So if the agent didn't send the measurement, the verifier can simply wait until the agent, for example, recovers connectivity and goes again and can send again the measurement. If it took too long, then it can authenticate it again to get a new token and start again pushing the measurement. So it's much easier to handle the intermittent connection loss. It has a smaller footprint since the agent doesn't include a complete web server implementation, and is much more scalable as the agent, we offload the scheduling and the initiation of the attestation to the device themselves, and the verifier don't have to track all the agents that it should be monitoring and asking for measurements all the time. So, okay, that was the change that we are making, and I would like to talk a bit about how the open source made this possible. So I always started with some discussions upstream because it was obvious for many people that the current architecture wasn't nice, especially when we started trying to implement our OpenShift operator to deploy the whole system. Then we saw, yeah, it would require a lot of workarounds because the agent's so exotic, let's say. And then finally, some upstream contributors from HP created the enhancement proposal upstream, and we, Red Hat, also were interested in this feature, right? So we offered help to implement because they were having difficulties, let's say, taking more time than they wanted and that we also wanted to implement it. So we offered the help, and it was the perfect marriage, let's say. So we split the work. They took over the responsibility for implementing the changes in the verifier and registrar part, which is the server part. And we, in Red Hat, we took over the responsibility of implementing the agent changes. So we create this open communication channel via the channel in the CNCF Slack instance. So it's public, everybody can join there, follow the discussions. We also created this publicly accessible project, which is basically a Kanban board where we put the cards, what we are working on, and the community can follow the development. And every month we have the community meeting, and we report the progress, what are happening, and etc. So it's really fruit of the collaboration in open source. So here I just took a screenshot of the project Kanban board. If you follow that QR code or the link that I put in the previous slide, you will get there in the our project page or dashboard of the Kanban board. And you can also follow this to get into our repositories. If you you are welcome to contribute. We need as much contributors as possible, right? It's always nice. So also you can join the CNCF Slack instance and join our channel to ask questions and follow the conversation there. So you are always welcome. And in conclusion, Keylime is moving from pull to push model that will make the life of edge IoT and cloud deployment much easier. And I think in architecture-wise, it's much cleaner. The open source is what made this possible through the collaboration that basically remove this boundary between companies so we can help each other and work towards a common goal. So please reach out to me if you have any use case, anything that you think could be the next feature for the project. And that's it. Thank you very much. So any questions? Please.
What happens with this push model in case of successful attestation, right? For example, for this IoT device, I might want to deliver some secrets to them, right? So
Right.
if they do it in a good state, they come to me, they attest, I want to give them a secret so they can join in some password, for example. Can I do that? Because it's like, okay, checkbox, but what's behind this?
Okay. So the question was if there is a mechanism to deliver some secrets once these devices come up and successfully attest. So this is a bit controversial. Currently, Keylime in the pool model, it supports delivery of secrets. So it's called the secure payload mechanism. So basically, you have a mechanism that you can encrypt some payload with some keys. I won't go into details how it's generated and encrypted, but this payload can only be decrypted when it passes attestation and receives from the verifier, OK, you can decrypt it. The thing is that many people saw that as a possible backdoor or front door, right? Because it's supported. So to deliver, because currently Keylime supports even executables that you can configure to execute remotely in the monitored systems once it passes attestation. So that is kind of not nice in like a secure point of view. So in the push attestation, we are not planning to implement something like that. So that would be kind of out of scope. And if you really need that, then please come to us, propose your enhancement proposal, and we can consider implementing it also for the push model. But I definitely won't implement it in the same way it is today because of many problems. For example, it would be simply impossible to get any FIPS compliance because the protocol that is used today in the pool model is custom and doesn't follow or doesn't use algorithms that are approved by FIPS. So if we decide that that's something that people really need and want, we can consider implementing it, but not in the way that it is today. So yeah, but thank you for the feedback because yeah, we were wondering if anyone would really require this to have it deployed. Any other questions? Please.
So I have the following question. When we have a full model, we can consider that the container doesn't respond for our attempt to attestation. Is compromised, and we can immediately react on this. In the push model, the possible delay of response is a part of protocol, and looks like it leaves much more possibilities for a bad actor if they manage to compromise the container. What am I missing?
So the observation, let's say, is that in the pool model, you can simply mark an agent that don't reply in time as a failing attestation, while in the new protocol, theoretically, you could compromise the agent and then get it back to sending measurements, but it's compromised. So
The agent or the whole container?
yeah, or the whole system that is running the agent. So I would say is the same problem, right? In the pool model, you wait for some time. If the agent, you try to reach out the agent a few times, and then you give up. Okay, I cannot reach. This agent is not considered in a good shape anymore, and trigger the revocation mechanism. In the push model, you could do or could have the same policy, right? If you don't, so the whole plan is that the verifier will tell the agent how long or what's the interval that it needs to send the measurements. If the agent doesn't send, then you simply mark it failing attestation and it falls into the same situation, right? But later, the agent can re-authenticate again and prove that it's still in a good shape and reestablish the connection and send the messages. So in this sense, it's much better in the push model because you don't need any intervention, external intervention, to re-enroll the agent there. So, yeah.
The attack surface big in case
Sorry, I couldn't get it.
Can we make a system simpler in a full mode, a verifier simpler in a full mode and push mode? Or they will be of equal complexity?
So the question is if in pull model the verifier couldn't be made simpler than in the push model. So the problem is not in the complexity in the verifier, but in the architecture itself, because if you need to reach out actively to the agent, so you have to go through these network issues that are, let's say, out of scope, right? So even though for us, Keylime, it's not much different, for people using it, deploying it, it is one less step, right, to configure the network, et cetera, et cetera. So in my personal opinion, it is not worth to try to make the verifier simpler because the main issues in the architecture won't be solved, which is the problem that the verifier has to actively reach out to the agents. So that is the main problem. That won't be solved by improving the verifier. You really have to change and reverse the protocol so that the agents reach out to the verifier. So, yeah. So we are out of time. So if you have any other question, you can reach out to me. Thank you.